Okay, and so please, at this point now, if you type your name into the chat, we'll get it recorded. So we have a record of your attendance so that you can continue to receive data. All right, so thank you again for coming. I hope you're all doing fine. And I want to talk today about kind of maybe, one of the most interesting parts of calculus because we're going to see, what derivatives and antiderivatives, how they're related and how they relate to this problem of finding areas, which kind of at first glance is you wouldn't necessarily think would be the case. But we're going to see something that I think today is pretty incredible. And it's all going to be based on this physics that we did last time, right? So everything is going to be based on how we did this relationship between speed and position and acceleration, and how we go back and forth between all of them by taking derivatives and by taking antiderivatives. Okay, so we'll review all of that so that everybone's on the same page. But then what we're really going to see today is what all of this has to do with areas, which is a
Yeah,
pretty great application.
hello, Alonso.
Hello? Yeah.
Sorry, this is Lawrence. Sorry.
Hi, Alexander?
Yeah, sorry. I had to join a meeting late because I attempted connection, but nobody was letting me in.
Okay.
So I had to come to Sandy's office. But I've been following the conversations, strictly between you, the bank, and then our team. So I think a lot have been said already.
Mhm.
So I just want to speak on the 19 schools that are ready and awaiting deployment of devices, as well as the 14 schools that are still facing challenges in completing the renovation. So for the 19 schools, um, we are keen to making sure that these schools the computers are deployed or devices are deployed before the deadline, the 24th, 31st on Monday. So what we have done is that while Planet PC is currently in Nima County to finish the 11 schools, they are hoping to finish the deployment of 11 schools today in Nima. That brought the total number to 122. So we've also had a discussion with the contractor this morning. So tomorrow and Saturday, they will be heading to commencing, they'll commence the deployment.
Okay. Yeah, I don't know if that was meant for us or not, but in any case, welcome to everybody. As general rule of thumb, please only unmute yourself if you're answering a question or asking a question. Okay, so let's get started because it's a little bit late. So I want to, recall what we were talking about last time, which is uh, we were talking about antiderivatives, right? So if you have a function, which we'll call little f, and then if you have another function, capital F of x, that capital F is called an antiderivative of little f if capital F prime is equal to little f. So if the derivative of big F is little f, then the antiderivative of little f is big F. So it's just reversing this process of differentiation. And we've seen also that if you have a particular antiderivative, then you can add a constant and it's still going to be an antiderivative, right? Because when you take the derivative of f of x plus a constant, you'll get little f of x from this part, right? You'll get little f of x when you take the derivative over here. And when you take the derivative over here of this constant, you're just going to get 0. So you end up just getting f of x plus 0, which is still going to be f of x. Okay. So you can always add a constant if you want, and that's still going to be an antiderivative. Okay. And a matter of notation, I didn't introduce this notation last time, but I will this time. We write that instead of just saying an antiderivative, you can also use this sign right here. This is called an integral sign. And the notation here is that you say, sorry, the integral of f of x dx is equal to capital F of x plus c. Okay, so what this means here is that this here is a function, and this here is the antiderivative. Okay, and for now, I'm not really going to worry about what this dx means. So let's just say that it's part of the notation for now. Okay, so an example of this notation that we've seen is if I say, what's the integral of 2x dx? Well, we saw last time that an antiderivative of 2x is x squared, so you would write that as x squared plus c. Use all of the possible constants. Okay, so this is red taking an integral. An integral means an antiderivative, or at the very least, this kind of integral means an antiderivative. This is called an indefinite integral. We'll see later today what a definite integral is and what that has to do with anything. But for now, these two words are just going to mean the same thing. So integral and antiderivative mean the same thing. Okay. When you do the integral sign, you write out all of the antiderivatives. Whereas if I just say I ask for an antiderivative, then I'm just asking for one. And what we've seen in these physics problems is that often you want one particular antiderivative that has a good property that's going to be useful for your physics problem. And so today we are going to be doing a lot of physics again, and we're actually going to motivate the fundamental theorem of calculus, which is the final result today. We're going to motivate it from physics. Okay, so everything's going to be tied into physics. All right. So so let's just go and do the homework problems first. This is going to be our review. So several people submitted homework solutions, so I appreciate that. So let's start. Oh, maybe before we do the homework, sorry, question, Deborah? No. Okay. So also just a review of what we did last time is we have these anti-differentiation formulas. So we saw with the power rule that to find an antiderivative for x to the n, when n is any number at all, well, not -1, but if n is any number other than -1, sorry, uh, so sorry. Yeah, so if n is any number other than -1, then the way that you take the antiderivative of x to the n is you have x to the n plus 1. You raise the exponent by 1, but then you also divide out by n plus 1. This is the formula we had last time, and then also plus an arbitrary constant. So an example, for instance, if I take n equals 2, this tells us that an antiderivative of x squared is going to be x cubed, and then you have a 1/3 on the outside plus c, right? So this is how you take the antiderivative of a single power of x. And then you can get more general functions by using these addition, subtraction, and constant multiplication rules, right? So if I have two functions that I'm adding, f and g, then the antiderivative of f plus g is just an antiderivative of f plus an antiderivative of g. Same thing with minus. If I have f of x minus g of x, then an antiderivative of the difference is going to be an antiderivative of f minus an antiderivative of g. And similarly, if I have a function f and I multiply it by a constant c, then to take its antiderivative, I multiply that antiderivative by the same constant c. Okay? So these are our basic rules for anti-differentiation. And there are tons more rules. There's integration by parts and trig subs and trigonometric integrals and partial fractions. And there's all sorts of different ways of doing these antiderivatives, which can get very complicated. We're not really going to focus on that. Certainly not today, but probably not at all this term. And the reason is that I think there's more kind of fundamental calculus that's worth learning rather than learning how to do a bunch of complicated integrals that a computer can do for you anyway. Okay, so we're going to really restrict to just these basic rules over here. Okay, so here's how you can take antiderivatives of polynomials and with one term, and then if you have a bunch of terms, you can combine them together by using these rules. Okay, so let's do an example to start with. So this homework exercise number 1 said find all, more typos here. Find all antiderivatives of 4 times x to the 2/5 minus 5 times square root of x. Okay. So what is the procedure here? Well, this is a difference, right? So we're just going to go take each term separately. Okay, so does anybody want to do this? And remember, by the way, if you haven't put your name into the chat to put it in, because it's only since I started the recording will it get recorded. Okay. Okay, well let's think about the power rule. If we want to find an oh, okay, that's fine. Um, that's fine. So if you want to find a an antiderivative of 4 times x to the 2/5, well, here we have x to the 2/5. Let's look at the power rule. It says if you have an exponent, you need to increase the exponent by 1. So what we're going to have here is x to the 7/5, but now you have to also divide out by that 7/5, right? So we're going to get 1 over 7/5 times x to the 7/5. And then, of course, we still have a 4, right? Because this 4 gets carried down. It's a constant multiple, right? So the term we get there is 4 times 1 over 7/5 times x to the 7/5 minus, right? Because the minus sign just gets carried down as a minus sign. And now 5 times square root of x, right? 5 times square root of x, of course, that's 5x to the 1/2. Well, 5x to the 1/2 is what? Well, again, you have to raise the exponent by 1. So you're going to get x to the 3/2. Then you divide out by 3/2. And then again, the 5 just comes along for the ride. So you have 5 times 1 over 3/2 times x to the 3/2. And then plus c to find all the antiderivatives. And now if you want to simplify this, that's 4 times 5/7 times x to the 7/5 minus 5 times 2/3 times x to the 3/2 plus c. And then further combining, you get 27ths times x to the 7/5 minus 10/3 x to the 3/2 plus c. Right? So this is the final answer that you're going to get. This is how you do these antiderivatives, right? It's fine that these exponents here are fractions, even if they were irrational numbers, that's fine also. The point is that you just always add 1 and then you multiply by the reciprocal of that same 1. Okay? So all of these here are perfectly fine. And you end up getting exactly this 27ths x to the 7/5 minus 10/3 x to the 3/2 plus c. Okay. And just in this other notation, just because I want you to get used to this integral notation also, we would say that the integral of 4x to the 2/5 minus 5 square root of x dx is equal to this answer, 27ths x to the 7/5 minus 10/3 x to the 3/2 plus c. Okay, so that's another way of saying this notation. Okay, is that this integral is equal to this expression right here. Okay. Okay. All right, any questions on this example? This is kind of straightforward application of the integration or anti-differentiation rules that we saw last time. Right? So we should think of this as just notation. This sign just means take the antiderivative, and for various reasons, you have to write this dx here. For us now, the dx is completely meaningless. You should think of it as just part of the notation. When you put this kind of elongated s here and a dx at the end, it means take the antiderivative. Okay. No questions on this?
Yes, sir.
Yes.
Afternoon, sir.
Okay, good. Yes, Prince. Hi.
Prince.
How are you?
Yeah, okay, thank you so much. I'm okay, sir. How you doing?
Good, good.
Okay. I have a I have a concern. I have a concern right here. We are in the problem we have 4s raised to the power of 2 divided by 5.
Hmm.
But during the solving, we have a 7 over 5. How?
Right. So this is because 2 over 5 plus 1 is equal to 7 over 5, right? Because you add 5/5. And in our formula for the power rule, when you're doing an antiderivative of x to the n, you always replace the exponent n with n plus 1. And then you also divide out by that same n plus 1,
Oh,
right? So the 2/5 gets raised by 1, that gets you 7/5, and then you have to have a 7/5 in the denominator here. Right. So this is what we have. So the 2/5 becomes 7/5, and then it gets
okay,
7.
okay, yeah, yeah. I understand that. I understand.
Okay, great. And that's how the 3/2 comes
Yeah,
also.
I understand that.
The 1/2 and you get 3/2. Okay, great. Other questions? Okay. Let's look at exercise 2. So again, a few people sent correct answers to this exercise. So find an antiderivative of 5x to the fourth minus 3x squared plus 6, but I don't want just any antiderivative. I want an antiderivative such that f of 1 is equal to 10. Okay, so I need a very specific antiderivative. Okay, so first we start by taking, so step one, we've seen these before, is take the general antiderivative. Okay, and so that's going to be step one that we'll do first. So if we want to do the antiderivative of 5x to the fourth minus 3x squared plus 6, well, what function gives you 5x to the fourth as its derivative? It's going to be a simple function. Or you can use the power rule that we wrote. That's fine also. Anyone?
Yeah,
Yes.
let's say 5 multiplied by
Mm-hmm.
1 over 5.
Mm-hmm.
Okay.
That's
X
going
raised
to
to the 5 power minus. We have
well, wait.
5.
So that's 5x to the fourth, right? So we have x to the fourth gives you 1/5 x to the 5. So what else do we have to multiply by here?
5.
5. Great.
5
Okay. Keep going.
minus
Mm-hmm.
3 multiplied by 1 over 3. 1 over 3.
Mm-hmm.
X to the third power
Mm-hmm.
plus, let's say, the constant C. That is 6.
Well, what about the 6? What's the antiderivative of 6?
So it's 0.
Yeah, 0.
Careful.
Okay.
Careful. The derivative of 6 is 0. But antiderivative,
Yeah.
we want something whose derivative is 6.
So can we say plus 6 minus 6 to get it 0?
Well, 6 gives you 0, right? But we want something whose derivative is going to give you 6, right? So what
That is
function, if you take the derivative, do you get 6 as your answer?
6x.
6x, exactly, right? And we
Yeah.
should think of this exactly, maybe this is what you're saying. 6 is equal to 6x to the 0. So the
Yes.
antiderivative is going to be 6 times 1 over 1 times x to the 1, which is just the same
Okay.
thing as x, right? So in general, when you take the antiderivative of a constant, it's just that constant times x, right? Because
Okay.
we know the derivative of 6x is 6. Okay, and then lastly, plus,
So we have 5/5, that is 1.
Right.
So we have x to the 5th power minus 3. There's a x to the 3rd power
Mm-hmm.
plus 6x
Mm-hmm.
plus c, the constant.
Right. That's great. So this
Yeah.
is perfect. Right. So we have x to the 5th power minus x to the 3rd power plus 6x plus c. Okay.
So substituting for f of 1 is equal to
Yeah,
10.
hello, guy.
Hello. Sorry. Is there a question before we move on? Yeah.
Yeah,
So we're not done. That's step
yeah,
one. Prince. Yep.
thank you. Prince,
Yep.
so I, we got rid of, if I may understand this, we got rid of the whole number by this fraction because factor one is 5 and divided by 1, which is just equal to 1. Is so I will level with s raised to the 5th power. Is that what we
Mhm.
did?
Yep.
Yes.
Mm-hmm.
Yes.
Exactly.
Okay.
Yeah. Yeah. So
Thank you.
we canceled out the 3s and we canceled out the 5s.
Yeah. So that cancel. Yeah.
Exactly. So step 2 is solve for c using f of 1 equals 10. Right? So we don't want just any antiderivative. We want a particular special antiderivative. Okay?
Yeah.
So Abraham, do you want to continue?
Yeah.
Okay.
So we said 10 raised to the 5th power.
Oh, careful. 10 raised. What are we punching in for x?
10 for x.
No, right? Because it's f of
For f of 1.
f of 1, right? So
F
we
of
have
1
to
is
punch
equal to
in
10.
1 for x, right? Because it's f of x.
Okay. So we say 1 raised to the 5th power
Mm-hmm.
minus 1 raised to the 3rd power
Mm-hmm.
plus 6 times 1
Mm-hmm.
plus 10, which is a constant
Well, plus c,
plus c. Yeah,
right, equals 10,
it's equal to 10.
right? Because this
Okay.
expression here, right, this is f of 1, right? I mean,
Oh,
this
okay,
expression
okay.
here, right, is f of x. And so if you punch in 1 for x, that means you to do f of 1 means you punch in a 1 for x everywhere here, and you want this to be equal to 10. That's
Okay,
exactly your equation
so
here. F of 1
so that is we are solving now to get a value for c.
exactly.
Okay. So we have x 1 raised to the 5th power, which is 1
Right. 1.
minus 1 plus 6 plus
So
c is equal to 10.
Exactly.
if
So
I
1
may
minus
understand. Hello.
Yeah.
Yeah.
1 minus
So
1 cancel.
it's because such that the f. Hello.
Yes. Hello, Prince.
Hello.
Prince. Yes.
So because such that f is equal to 1, and f of 1 is why everywhere we see s raised to the 5th power, we represent it as 1,
Exactly.
raised to the 5th power. Okay.
Mhm.
Okay.
So everywhere you see
So
an
it
x,
means
you
that,
replace it with 1, right? Because if this is
okay.
f of x, then f of 1 means every time you see an x, put in 1 instead,
Okay.
right? And you need
So,
that whole thing
definitely
to
it
equal 10.
means to just calculate now the value for c, which
Right.
it means we have to find the value for c,
Right.
and c will be equal to 4 if I say it's this. Yeah.
Exactly. So c is equal to 4, which means the actual answer to the question, right? We want to find the correct antiderivative such that f of 1 is equal to 10. Well, it's just this expression here, but with c equals 4, not with a general c, right? So to get this to work out, so the final answer over here, I need a little extra space here. The final answer is going to be f of x is equal to x to the 5th minus x to the 3rd plus 6x plus 4. Okay, this is your final answer. Okay, maybe I could call this step 3. Okay. Okay, so you take a
Yes.
general antiderivative, that now you use the equation to figure out what c is, and then you go back and write down your general antiderivative, but with the correct c instead of just an arbitrary c, you write it down with the correct c that you solved for.
Yeah, the
Yes, Prince.
yeah, okay. You said this is a answer, but we working in equation. So if we say x raised to the fifth power minus x raised to the third power plus 6x plus 4, everything all equal to 0, will it be correct also?
No, because we're not setting it equal to 0, right? I mean, if you wanted to find a
Okay.
root of this, then you would set it equal to 0. But there's nothing in the problem about 0, right? We're just asking, the problem's asking to find a function, to find this antiderivative f of x as a function. So this is the correct function. We're just writing down the function x to the fifth minus x to the third plus 6x plus 4. If I just do a general antiderivative, this isn't just one function, but it's a lot of different functions depending on the value of c. But for us, there's only one correct value of c. That's c equals 4. So you have to have c equals 4 in order to do the function correctly.
Okay. Thank you so much. It's well
You're
understood for
welcome.
me.
Yeah, and this idea of finding a specific antiderivative is going to be very important for all the physics problems. So that's why I want one, abstract version first, and then the next exercise will be the same thing but involving physics. All right, any other questions on this example?
Yeah, another question that
Yeah, Prince.
yeah. So this rule is applied to antiderivative, but if for any reason we ask to only calculate the derivative of this expression,
Yeah.
we're not going to come so far to this, right?
Yeah, if you're doing a derivative, you don't have these
Mhm.
c's. You don't have to worry about these c's, right? You just take the derivative. So if I just asked you to do
Okay.
the derivative of 5x to the fourth minus 3x squared plus 6, you would just do it. You would get 20 times x to the third minus 6x plus 0. And that would be
Okay.
that. There's no freedom anymore. I'm accepting, sorry, 1 second. Okay. So, great. All right, several people keep asking to be joined, and I keep accepting them, but there seem to be some issues. So, okay. But when you take an antiderivative, you have a lot of choices. So, depending on the problem, you might need to make a specific choice. Okay. All right. Any other questions on this exercise? Okay. Let's move on to the next one. So before the third exercise, I just want to review what we talked about last time, the relationship between anti-differentiation and motion in physics. So the situation is we're given an acceleration function that we call a of t, right? We're giving an acceleration function that we call a of t. Okay. So we call it a of t, and we know that you can determine the velocity function by taking an antiderivative of a of t. Right? The velocity function is the antiderivative of the acceleration function. And usually there's some information in the problem that tells you, is the whiteboard screen not being shared? It looks okay to me. Are people seeing the whiteboard?
For me, I've seen it share. For me, I've
Okay.
seen it.
Okay, Robert, I think you're the only one who's not seeing it. You may need to log out and log in again.
It is visible. I'm looking at it.
Invisible, right?
Yeah.
Yeah, okay. Um, so, and then once you have the velocity function, then you can take the antiderivative again to determine the position function. Remember, we go from acceleration to velocity to position by taking an antiderivative each time. And this is because in the other direction, you would go from position to velocity to acceleration by taking the derivative. So each one of these is a derivative, and in the opposite direction is an antiderivative. Okay? And which antiderivative do you take? Well, it's going to depend on the problem, but usually the problem will have some conditions that tell you what to do. Okay. So, this being known, now let's look at the homework exercise. Okay. So, the homework exercise says a car is traveling at 88 feet per second. It's pretty fast, it's about 60 miles an hour. And then the brakes are fully applied. And when you do that, it produces a constant deceleration. That means a negative acceleration of 22 feet per second, feet per second squared. And the question is, how much distance is traveled by the car before it comes to a stop? Okay. So what we need to do is figure out, for all of these physics problems, what we need to do is we need to figure out A of t, V of t, and S of t. Okay, and we figure we'll take t equals 0 to mean when brakes are first applied. Right, that's going to be what t equals 0 means. Okay. So first of all, what's the acceleration function? Well, it says there's a constant deceleration of 22 feet per second squared. So for the acceleration function, it's constant. It's just minus 22, right? This is a constant. Or at least it's constant until the car comes to a stop. Right? This is kind of decoding what the word problem says. Constant deceleration is 22 feet per second squared. Is that okay?
Okay.
Yeah. Okay. So
Well,
now we need,
are that all right?
yes, question. There's a question? If you have a question, you're on mute. I can't hear you.
Hello.
Hello, yes. Abraham.
Yeah, I'm saying the unit is not attached to the number, just minus 22.
Yeah, I mean, we could say I can write it as feet per second squared if I want to. I mean, that's fine. We're going to do everything in terms of feet and seconds, so we don't necessarily need to write the unit. But if you want to write the unit, that's fine. We can write feet per second squared.
Thank you.
Okay, you're welcome. Okay, so now we have to go up one step to find the velocity function, right? We take an antiderivative. And so the antiderivative of minus 22, we've already seen that's minus 22t, but plus c. Okay? I mean, this is how an antiderivative of minus 22 is easy. It's just minus 22t. But we know that we also have to add c. And now we have to know what is the correct c, right? What's the correct c that we want? Well, we have to use some information from the problem. And we know that at time t equals 0, this is when the brakes are first applied. How fast is the car traveling? Well, it's traveling at 82 feet per second, right? So in particular, we have the condition from the problem is that v of 0 at time 0, when the brakes are first applied, this velocity is equal to 88 feet per second, right? So this is our expression for v of t. We're trying to put in v of 0 equals 88. So we get an equation which says negative 22 times 0 plus c. This is v of 0 should be equal to 88. Sorry, 88. 88. And this tells us that c is equal to 88. right? So what we actually get is that v of t equals minus 22t plus 88. Okay, so that's the correct velocity function. Okay. So when we're doing these velocity functions, it's in two steps, just like the last problem. First, you take an antiderivative. That gives you minus 22t plus c. And then you need to figure out what is the correct c. Yeah, so James, that answer is correct. We'll see how we get that. So that is the correct c. But the way we know what the c is we have to punch in a condition from the problem. We have to look at the problem to see what we can say about this velocity. And what we can say about the velocity here is that at time 0, it's 88 feet per second. And that's going to be enough to give us an equation to solve for c. Okay. Are there any questions about how we found this velocity function? Okay. All right, so this is our velocity function, minus 22t plus 88. So we do the same thing to find the position function. It's another antiderivative. This gives us s of t. Well, the antiderivative of t we know is 1/2 t squared. That's our power rule. And then the antiderivative of 88 is 88t, and then plus c again. And simplifying this, this is minus 11t squared plus 88t plus c. And we again need a condition. Maybe I should write these conditions in another color just to distinguish them. So our condition. So now over here, what's our condition? Well, my condition here is basically just going to be that s of 0 is equal to 0, right? All I'm saying is that at time 0, we're going to assume that the position is 0. Okay, we can basically call that position whatever we want. As long as we call the position what we want, we just know that when the car stops, whatever that position is going to be exactly how far the car has traveled. Okay, so if we take s of 0 to be 0, what does that tell us? That tells us that minus 11 times 0 squared plus 88 times 0 plus c is equal to 0, and that's going to imply that c is equal to 0. So what we really get here is that s of t is minus 11t squared plus 88t. Okay. Okay. All right, great. Okay, so I mean, James, this is going to be correct, but we're going to see why this works. Okay? So no, I know there's physics formulas involving v squared, initial velocity squared, final velocity squared, but why do these formulas work? They work because of this methodology here. They work because of this calculus. So what have we done? We have found two functions. We found a velocity function. Oh, actually, let me not box that one. We found a velocity function, minus 22t plus 88, and we found a position function, minus 11t squared plus 88t. Okay? So now the question is, how do we use this to actually answer the question? So with all these physics questions, you want to find out the acceleration, velocity, and position. But once you have that, now you need to use this to answer the physics question. And the physics question is, how much distance is traveled by the car before it comes to a stop? Okay. Well, we know that the velocity function is minus 22t plus 88, right? So the car coming to a stop means that the velocity is 0. So we need to solve, when is this equal to 0? Right? So maybe I'll start a new page with this, right? So I have that the velocity of t is minus 22t plus 88, and the position function of t is minus 11t squared plus 88t, right? So, okay, when does car come to a stop? When does the car come to a stop? Well, we need to solve for when the velocity is equal to 0, right? So we need 20 minus 22t plus 88 equals 0, right? 0 means a stop. So that's going to tell us that 88 equals 22t, which is going to tell us that t equals 4 seconds. So in this case, it takes the car 4 seconds to come to a stop. So the second question is, where is the car at t equals 4? Well, to do that, we've got to plug in 4 for s. Well, s of 4 is going to be negative 11 times 4 squared plus 88 times 4. And that's going to be, it's going to turn out to be negative 176 plus 88 times 4 is going to be 352. And in the end, this comes out to be 176 feet. Okay. This is going to be the final answer. Okay, so the way we did this problem was we wrote down velocity and position functions using calculus. And doing that, we had to do antiderivatives and also find the right antiderivative by using a condition in each case. So it gave us a velocity function, and it gave us a position function. All that we were given was the acceleration. That's enough to get us velocity and to get us position. So now that we have velocity and position, we look at the problem. It says, how far does the car go before coming to a stop? Well, we can figure out how much time it takes the car to come to a stop by the velocity expression. That's just a stop, right? Means v of t equals 0. So we solve for t. That gives us t equals 4. And now once we have that, we can plug that in to find what is the position of the car when it comes to a stop. So at time t equals 4 seconds, well, we plug that in for s, and we show that the car has moved 176 feet at the time that it comes to a stop. All right. So that's the answer, 176 feet. Now, there are other physics formulas that will let you do this. One of the problems with these formulas is that they only apply for constant acceleration, whereas this method will apply for any acceleration function. Okay, so if you do this using calculus and antiderivatives, even if the acceleration is not constant, it will still work. Okay, any questions about how we solve this? Okay, any other questions? Needs to look better. Okay. Okay, let's go on. So what are we going to do today? What's the new material? Well, we want a geometric interpretation of what's called the distance problem. So this material, if you want to look at the textbook, it's going to be drawn from sections 4.1 and 4.3 of the textbook. Okay? So what is the distance problem? The distance problem says, suppose an object travels in a straight line and its velocity function v of t is known. And then the question is, if we have two times, time A and time B, how far is the object at time B from where it is at time A? Okay? And so this is a problem we already know how to solve because we know that the position function is an antiderivative of the velocity function, right? This s of t, we find it from the velocity function by taking an antiderivative. And we want to know how far is the object at time b from time a. So the quantity we want to calculate is s of b minus s of a. And maybe that's a negative number if the object's moving backwards. So what we really want is the absolute value of s of b minus s of a. And something else to notice is that no matter what antiderivative we take, this s of b minus s of a is going to be the same, right? Because if I have here s of t, I get s of b minus s of a. But if I take another derivative, maybe given by another antiderivative given by s of t plus c, so if these are my choices of antiderivative, sorry for the writing being small, choices of antiderivative. If these are my choices of antiderivative, then what happens when I punch in b and a to s of t plus c? I just get s of b plus c minus s of a plus c. And this is just s of b plus c minus s of a minus c. And this is also equal to s of b minus s of a. So it turns out when calculating, and these two are equal. Okay. So when calculating these distance traveled problems, it doesn't matter what antiderivative you take. Even if you add on some constant, it's just going to get canceled out in the end. Okay? So that's good news. That means we never have to worry about what the right antiderivative is when solving this question. We can just use any antiderivative we want, and it's going to work. Okay, so if we know the velocity function, we just take an antiderivative and we figure out what the position is going to be. Okay, and with this antiderivative, we get a position function, and to find the distance traveled, we do s of b minus s of a. Okay, so let's look at this in a really, really easy example. So we're going to do the easiest example possible. Okay, so suppose a car travels at 30 miles per hour in a line. How much distance is traveled from time t equals 0 hours to time t equals 3 hours? Now you know this is an incredibly easy problem. You don't need any calculus to solve this problem. But I want to do this problem very carefully because it's going to show us eventually how other things work, right? So first of all, I want to do what's the calculus solution? Even though this is kind of overkill, you don't really need a calculus solution. But what would be the solution if we used calculus? Well, I would have that v of t is equal to 30, right? The velocity is 30 miles per hour. And so that means s of t, my position function, I can just take to be an antiderivative of 30, which is going to be 30t. And remember, we don't need to worry about the constant because for figuring out the distance traveled, the constant's not going to matter. So if s of t is 30t, then I want to know how much distance is traveled from 0 to 3. That just means I want to know how far is the position at 3 hours away from the position at 0 hours. So what I'm looking for is, so the distance is s of 3 minus s of 0, which is equal to 30 times 3 minus 30 times 0. And that is equal to 90 miles. Right? So if we had to use, I'm going to call this calculus. Of course, you would never use calculus for this problem. You would just say, oh, distance times time. Distance times rate, rate times time equals distance. So you would say, oh, it's 3 hours, 30 miles an hour. That gives you 90 miles. But I just want to show that even though it's a little overcomplicated, you can do this with calculus if you want, right? So this is going to give you an answer of 90 miles. Okay. Now, what's the basic solution? Of course, the basic solution is just rate times time equals distance. And that tells you that 30 times 3 equals 90 miles. 30 miles per hour times 3 hours is equal to 90. Maybe let me write it down. Let me just write the units down more carefully. So 30 miles per hour times 3 hours is equal to, we cancel out the hours, and we're left with 90 miles. Okay, so this is either of these is a perfectly good solution. They both give us the same answer. But the reason I want to do both of them is I want to show what this means graphically. Graphically, let me graph the speed on axes. So the horizontal axis is going to be my time axis, and the vertical axis is going to be my velocity axis. And so what I have here is a velocity of 30, and my time goes up to 1, 2, 3, and I just have a constant velocity of 30. And if I do this, then this area is equal to 30 times 3, which is equal to 90, right? So from this rate times time, what we see is that the area under the velocity curve is the distance traveled. I'll just say is the distance. Okay, so the area under the velocity curve is the distance. Okay, so this is a very easy question, but I just want to show that there's a few different ways of doing it, which all give you the same answer. So you have this calculus interpretation. You have this just standard basic solution, pre-calculus solution. And what we see is that that pre-calculus solution, if we look at it graphically, it actually corresponds to an area. We have 30 is the height and 3 is the width. And so you multiply them together and you get the area of this rectangle. Okay. Any questions about this? It's supposed to be very easy, but I just want to make sure that everybody sees these different ways, because for our next examples, these ideas are going to be important. This fine? Okay, great. Okay, let's do another example that's only a tiny bit harder. So suppose that a car travels at 30 miles an hour for an hour and then 20 miles an hour for another 2 hours. What's the total distance traveled? Well, in this case, I'm going to do the basic solution first, right? So basic solution. Well, here we have that the speed changes, right? So we have the first hour is, the distance. Well, it's going to be 30 miles an hour times 1 hour. And then plus, now we have 20 miles an hour times 2 hours, right? The hours cancel out, and what we're left with is 30 miles plus 40 miles. Plus 40 miles. It's 20 times 2 equals 70 miles. Okay. And for now, I'm not even going to do a calculus solution, but let me just look at this graphically. What happens here? Well, it's the exact same thing. If this is my time axis and this is my velocity axis, I do time 1, time 2, time 3, let's say 10. I'm just going to use different scales on my axes. So one is 1, 2, 3, one is 10, 20, 30. So we have that the car goes 30 miles an hour for the first hour and then 20 miles an hour for the next 2 hours. And so if we look at the entire area under this graph, we get a rectangle here. This is 30 times 1, 30 by 1. And then another rectangle here, which is 20 by 2, right? And the total area under the graph is, again, 70, right? So the total distance is again 70, right? 30 miles in the first hour, and then 40 miles in the next 2 hours because it's going 20 miles an hour, right? So the total area under the graph is again going to be 70 here. Okay, so notice again that total area under the graph equals the total distance traveled. Let me not just say under the graph, but under the graph of v of t equals the total distance traveled. Okay. Okay. So the total area under this graph is 70, and not only are they equal, but they're equal because you calculate them the same way. It's going at a constant speed 30, so you have 30 times 1 for the first hour, and then you have 20 times 2 for the next 2 hours. 70 miles, that's exactly the calculation we do here to calculate the distance. Okay. All right, so again, not terribly hard. We just have a little change here. All right, any questions on this?
That about?
Yes, Abraham.
Oh, okay, I understand. That is I'm looking at something on the graph because the second graph is stretched on the time. It's stretched up to 3.
Right.
But then see, it starts from 1. That is the area between 0 and 1 is not there. I was stretched up to 3.
Exactly. It's just this first rectangle and then this second rectangle. Right, because the first rectangle represents the first hour when the car's going 30 miles an hour, and then the next rectangle represents the next 2 hours when the car's going 20 miles an hour. Okay, so I promise this is somewhere. Sorry, James, yes?
So you add 30 plus the 40, I will give her the 70.
Exactly, right. I'll label these, right? 30 times 1, which is 30, and 20 times 2, which is 40 here. Right. So I promise this is getting somewhere. This is actually getting to a very, very serious theorem in calculus. But we're building our intuition with these basic examples that don't need any calculus, right? That you don't need any calculus to solve this problem. This is just an algebra problem, right? Okay. So now let's go to the next example where the ideas are really going to come. So over the course of 5 seconds, a runner steadily accelerates from 0 meters per second to 10 meters per second. And when I say steadily, I mean constantly. It's a constant acceleration rate. How much distance does the runner cover? And so the first thing, we're going to solve this problem 2 different ways. And this is going to lead us to the fundamental theorem of calculus. Okay? So the first thing is we can solve this problem using antiderivatives exactly the same way that we did the homework problem, right? So let's do the same thing. We have our acceleration is what? Well, the acceleration is what? Well, over the course of 5 seconds, it goes from 0 meters per second to 10 meters per second. So the acceleration is going to be 10 meters per second divided by 5 seconds, and that's going to be 2 meters per second squared. So it's a constant acceleration. That's what I mean by a steadily accelerates. So it's a constant acceleration of 2 meters per second. 2 meters per second squared. So now we can do the same thing that we did before. The velocity function is now going to be 2t plus c. We take an antiderivative, right? But here we also have a condition. Well, this runner is starting a race. So at time 0, the runner is standing still. So he accelerates from 0 meters per second to 10 meters per second, right? So the condition here is going to be that v of 0 has to be 0. At time 0, the runner hasn't started yet. And so that tells us that 2 times 0 plus c is equal to 0, right? Because this is our v of 0. And solving this for c, this leads us to see that c is equal to 0. Okay, so the real velocity function is equal to 2t. Okay, so the velocity at time t is 2t. And so now we want to know how much distance does the runner cover? Well, I take s of t. This can just be an antiderivative of 2t, which now you see is t squared. So James, your answer is correct, but what I really want to see is how this happens, right? So s of t in this case is going to be t squared. Okay, that's an antiderivative. And remember, when we're doing these change in positions, we don't care about what the constant is. Okay, so we're just going to have t squared, and then the distance is s of 5 minus s of 0, and that's equal to 5 squared minus 0 squared, and that's equal to 25. So it's going to be 25 meters. Sorry, meters. 25 meters. Okay. So this is the calculus solution, right? The point is we have a velocity function, and once you have this, you take antiderivative and calculate value at beginning and end. Okay, take antiderivative, I'll say, of v of t, and you calculate the value at the beginning and the end. Right, so this is just an easier version of our homework problem, right? Once you know what the velocity function is, you figure out the position function, you calculate its value after 5 seconds and its valuation at the beginning, and the difference between those two things is the distance traveled. So it's going to be 25 meters in this case. All right. Any questions on the calculus solution here? Okay. So now, what's the other solution? Well, same question. Same exact question. Over the course of 5 seconds, a runner steadily, which I mean constantly, runs from 0 meters per second to 10 meters per second. So how much distance does the runner cover? Well, what I want to do now is relate this to the area under a curve. So I'm going to do my same thing. This is my t-axis. This is my v of t axis. And I'm going to draw my function v of t. So we have 5 seconds, 1, 2, 3, 4, 5. And then here I'm just going to write my axes as 2, 4, 6, 8, 10. And what we see is we have basically a constant line, straight line going up here, right? This is the equation v equals 2t. This is our velocity function that we had before. Okay. So now, what could you do? You could approximate the distance traveled by saying, well, maybe the runner's going maybe at, 0 meters per second for the first second, 2 meters per second for the second second, 4 meters per second for the third second, 6 meters per second for the fourth second, and 8 meters per second for the fifth second. Right? This is not going to get you the exact right answer. This is going to get you an approximation. This is basically saying I'm going 0 meters per second for the first second, 2 meters for the second one, 4 meters per second for the third one, 6 meters per second for the fourth one, and then 8 meters per second for the fifth one. Right? And if we look to actually calculate how much distance this is, that's going to just correspond to the area of all of these things. So in this case, right, the total distance would be equal to 1 times 0 plus 1 times 2 plus 1 times 4 plus 1 times 6 plus 1 times 8, which would give us 20 meters, right? So it's an underestimate, right? Because for each of these, well, if it's 0 meters per second for the first second, and 2 for the second, and 4 for the third, and 6 for the fourth, and 8 for the fifth, the total distance traveled is just 1 second at each of these speeds. So we're going to get 1 times 0, plus 1 times 2, plus 1 times 4, plus 1 times 6, plus 1 times 8. Okay. But of course, this is not exactly right, because the runner isn't really going 0 meters per second for the first second. The runner is steadily speeding up from 0 to 2 over the first second. And then in the second, the runner is speeding up from 2 to 4. And over the third second, the runner is speeding up from 4 to 6, and so on. Right? So a better approximation would be as follows. Maybe 0 meters per second for the first half second, and then 1 meter per second for the second half second, and 2 meters per second for the third half second, and so on. And on this graph, that thing would look like this. It's going to look like the green over here. So at the second half second, it's going 1. Third half second, it's going 2. For the fourth half second, it's going 3. For the fifth half second, it's going 4. For the sixth half second, it's going 5. Seventh half second, it's going 6. And the eighth half second is going 7 meters per second. The ninth half second is going 9 meters per second, 8 meters per second, and the last half second is going 9 meters per second. So what it looks like, I mean, don't worry about the numbers so much, but what you're doing by dividing it into kind of smaller intervals here is you're doing a better approximation. You're not saying the runner's going 0 speed for the first second. You're saying 0 speed only for the first half second, and then at 1 meter per second for the second half second. So it turns out this is going to be an exercise, but this is actually going to come out, if you do it this way, you're going to get that the total distance in this case is going to be equal to 1/2 times 0 plus 1/2 times 1 plus all the way up to 1/2 times 9. And it turns out that what you get from this is 22.5 meters. It's a better approximation to the actual answer, right? If you do the approximation where you just take a snapshot of the speed every second, you get 20 meters. Now we're taking a snapshot every half second. That's a little bit better. And that gives us, in this case, 22.5 meters. We know the actual answer is 25, right? We solved this already on the previous page. The actual answer is 25. But this is giving us 22.5. And graphically, what's happening is that the green is a better approximation to the area under the curve, right? Or maybe I'll say to the area under the graph than red. Right? So the green is a better approximation to the area under the graph than red. And that's because when we're trying to, and that also coincides with the fact that our snapshots are faster for green, right? So we're showing, we're getting a better approximation to how the runner's actually going. We're taking a snapshot every half second instead of every second. So the idea is, and I'm not going to draw this, but imagine if we took a snapshot every quarter second of how fast the runner was running. I'm not going to draw it because it'll make it messy, but we'd get these even skinnier rectangles, which are going to get us an even better approximation for this area under the curve. And the idea is how much, and these are all approximations to the total distance traveled, is the area of these rectangles. But what's the actual total distance traveled? Well, from this, it seems pretty reasonable, and I'm not going to do a rigorous mathematical proof, but hopefully I can convince you that the actual distance traveled should just be the total area under the graph, just like it was in all of these other cases. Remember, over here, the total distance traveled was the area under the graph. For the next solution, next problem, the total distance was the area under the graph. And so in this one, the total distance should also be the area under the graph. And we see that we get closer and closer to that area by taking narrower and narrower snapshots. Okay? So the upshot of this is that the total distance traveled, if you want the exact right answer, you don't take these little approximations, but you actually have to take the complete area under the graph. That's going to give you the total distance. So if you have a velocity graph, the distance traveled is the area under that graph. Okay, and this should be believable. Okay, because you see by taking little approximations, you almost get the full answer. And so if you want the actual full answer, you can't take these little approximations. You've got to take the whole area. Okay. So what do we have? So this previous example suggests that we can determine the area under a curve by using anti-differentiation. Let me actually say one more. Let me give one more intermediate step before I say this. Right. So the idea is two ways to determine distance from v of t. So the first way is by taking s of b minus s of a, where s is an antiderivative of v. And the second way is look at the area under the graph of v of t. Right? So both of these tell you the same thing. They tell you the difference. Sorry, the distance. So this means that s of b minus s of a equals the area under the graph of v of t. Right? These are both ways of calculating the distance, one by calculus, one graphically, but they have to give you the same answer, right? Because they're both telling you how much distance is traveled. So we can kind of cut out the middleman entirely. Don't worry about the velocity thing. What we're showing is that if you have a graph, if you want to calculate the area under the graph, that's the same thing as s of b minus s of a, where s is an antiderivative of your graph. Okay. So the point is we can just do this in general, right? So this works for any graph because any graph could be a velocity function, right? So it's totally fine no matter what your graph is, even if it doesn't represent velocity. So what does that mean here? So the area under the curve via anti-differentiation is what? So this previous example says that we can determine the area under a curve using anti-differentiation. So specifically, if I have any function, y equals f of x, and I want to understand the area under that graph between x equals a and x equals b, so if I have some graph here, y equals f of x, think of it as representing a velocity. Well, the area under the graph is the total distance traveled, and that's going to be the same thing as take an antiderivative, evaluate it at b, minus take an antiderivative and evaluate it at a. So this is the kind of calculus solution. And this here is the, kind of, physics solution. It's the total distance. Okay. And so what this tells us is that you can evaluate the area under a graph, which represents a total distance traveled, by taking an antiderivative and evaluating it at the right endpoint, which is b, minus evaluating it at the left endpoint, which is a. So the fact that you can do this is what's called the fundamental theorem of calculus. It says that you can evaluate the area under a graph by taking antiderivatives. Okay, and this is a very serious theorem. And by the way, evaluating this is called a definite integral. So this here is just notation. There's no new ideas. It's just notation. If I write the integral of f of x dx, but instead I put a little a and a little b here, what that means is I take f of b minus f of a, where f is some antiderivative. Okay, so I'm sorry that a number of people who were at the beginning of class are not here anymore, because this is really, maybe the most important result in all of calculus. Okay, which is that you can relate antiderivatives to areas this way. And the reason it works is because of this physics interpretation, is that both sides are giving you a total distance traveled, right? If this is a velocity function, the area under it is the total distance traveled, and capital F of B minus capital F of A is also the total distance traveled. So they need to be the same thing. Okay. So, but now you can still use this outside of physics. It's just telling you that the area under any graph, you can figure it out by using antiderivatives. Okay? So let's do some examples, right? So example, let's say we want to determine the area under the curve y equals sine x from x equals 0 to x equals pi. Remember what that looks like. If this is x and this is y equals sine x from x equals 0 to x equals pi is just one hump of the graph, right? If I want to know what is the area, well, the area is equal to, by definition, it's going to be the integral from 0 to pi of sine of x dx. But if this notation is new to you and you don't like it, what this just means is find some f of x, an antiderivative of sine of x, and then evaluate f of pi minus f of 0. That's all that this notation means. It means find an antiderivative and evaluate it at pi and evaluate it at 0 and subtract. Okay, so what's an antiderivative of sine of x? What function, when you take its derivative, gives you sine of x? Yes, Abraham?
I say cosine of x.
Well, so remember, the derivative of cosine of x, remember d dx of cosine of x, so we calculated this a while ago, is actually negative sine of x. So if we want something whose derivative is positive sine of x, what do we have to do? Instead of taking cosine of x, we take so if derivative of cosine is minus sine, then whose derivative is just going to give us regular sine? Right, well, d dx, if I put a negative cosine here, that should be equal to negative sine x, right, which is equal to sine of x. So in fact, to do an antiderivative, you need negative cosine of x, right? Because the derivative of cosine is minus sine. So the derivative of minus cosine is going to be sine. And so the area is now just going to be capital F of pi minus capital F of 0, which is going to be negative cosine of pi minus negative cosine of 0. Well, cosine of pi, if you remember your unit circle, right? Pi is the angle all the way over here, and the cosine is the x-coordinate. So cosine of pi is -1 minus, and then minus cosine of 0. Cosine of 0 is just equal to 1. And so this is equal to 1 minus -1, and this is equal to 2. And so that's the answer. The area under one hump of the graph of sine is just equal to 2. Okay. And so this is, of course, an area that would be very hard to compute. You don't have any geometric formulas for this. But for calculus, you know that the area under one hump of this graph, you just have to find an antiderivative of sine. That's going to be negative cosine. And then you plug in the right endpoint, plug in the left endpoint, and subtract. And remember, what this means is that if you traveled with a velocity of sine of t from time 0 until time pi, your total distance traveled would be 2. Okay, and that's exactly this area under the graph. Okay, so you get this very nice answer. It's just 2 over here. Questions on this?
Thank you.
All right, James, you're welcome. Maybe I should just say for this earlier example over here, remember, what is the total area? This is actually a right triangle with a base of 5 and a height of 10, right? So the actual area, maybe I should write this over here, right? Actual area is equal to 1/2 times 5 times 10, and that's equal to 25, which is exactly the answer we got by calculus, right? So the actual area here of this triangle is going to be 25 because you have a base of 5, height of 10, and it's a triangle, right? So these are better and better approximations, 20 and then 22.5. The full area here is 25. Okay, so I forgot to say that. So let me say that now. And 25 matches what we got by using calculus over here. Okay, so that's the area under curve sine of x. Let's do another example. Determine the area under the curve y equals x squared from x equals 1 to x equals 3. So again, I'm going to draw this. 1, 2, 3. I have my parabola, y equals x squared. At 1, it's going to be 1. Here, it's going to be 9. And we're looking to find this area, right? Again, this is not, it's area under a parabola. This is not something that we have formulas to do, right? The only thing we can do is use calculus. So let's let capital F of x be an antiderivative of x squared. That's our graph, right? This is y equals x squared. Well, we know how to take an antiderivative of x squared, right? This just gives us that f of x equals 1/3 x cubed. We know this by the power rule. So what does this tell us? F of x is 1/3 x cubed. So the area, we take f at one endpoint, subtract f at the other endpoint. So f of 3 minus f of 1, which is 1/3 3 cubed minus 1/3 1 cubed. That's going to be equal to 1/3 times 27 minus 1/3 times 1. And this is going to be, that's 1/3 times 27 minus 1. And that's equal to 26 over 3. Okay. So this is the area here. So actually doing these problems is pretty easy. As long as you can find the antiderivative, then you can calculate all these areas however you want. Now, of course, the hard part is finding the antiderivative, right? But if you can do the antiderivatives, then you just have to punch in the right-hand endpoint and punch in the left-hand endpoint and take the difference. Okay, the hard part is justifying why this works. And the thing to take away is remember that this works because both the antiderivative method and the area method are telling you total distance traveled, if that's your velocity function, right? So the antiderivatives give you total distance traveled, and calculating the area also gives you total distance traveled. Okay, so since they both give you the same thing, they have to be equal to each other. Okay, so in this case, the area under this curve is equal to 26/3, which makes sense, right? Because if you think about this curve, right, if you looked at it as a rectangle, this entire rectangle would be 9/2. That would be have area 18. And we see because this is concave up, the area looks like it's a little bit less than half of the area of the rectangle. So that makes sense. It's a little bit less than 9, a little bit less than 18. So our answer makes some sense. All right, questions on this example?
Yeah, that,
Yes. It's okay, Prince? Yeah.
yeah. I have a question because the statement which y is equal to s squared from x is equal to 1 and to a is equal to 3. So
Hmm?
can we find in between of s1 s is equal to 3? Can we find s2 which is a is equal to 3? Can it be found too?
I mean, you can, but you don't need it in order to answer the question, right? Because this is like imagine a velocity question where your velocity is t squared from time t equals 1 to t equals 3. And you want to know how much distance is traveled, right? And so the distance is going to be find an antiderivative, which is going to be 1/3 t cubed, and evaluate that at 3 and evaluate that at 1 and take the difference. So if you wanted to do 2, that would be fine, but that would just give you the area between x equals 1 and x equals 2 instead. But the question
Okay.
asks for x equals 1 to x equals 3, so that's what you use. Okay. Yes, the James asked, can it be converted to decimal? Of course it can. It's 8.66666. Okay.
All right.
All right. So let's do the last example for today. So it can be shown. So taking antiderivatives is a little bit complicated. So take my word for it that it can be shown that an antiderivative of the square root of 1 minus x squared is given by this complicated expression. 1/2 x times square root of 1 minus x squared minus inverse tangent of square root of 1 minus x squared over x plus 1. Fine. Just believe me that if you take the derivative of this, you get exactly the square root of 1 minus x squared. You can't quite verify this on your own because we haven't actually discussed derivatives of inverse trig functions. So you're going to have to take it on faith that this is true, that if you take the derivative of this, you get the square root of 1 minus x squared. So the question is, we want to use this to determine the area of a circle of radius 1. Okay, use this to determine the area of a circle of radius 1. Okay, so what I'm going to do is the following. Okay, so what happens if I write a circle of radius 1? If I draw a circle of radius 1, circle of radius 1, well, if I can determine a quarter of the area, then that's good enough, right? Because if I know what the area of a quarter of the circle is, then I know the area of the entire circle. So we know that the equation of a circle of radius 1 is x squared plus y squared equals 1, right? That's the equation. But if I solve for y, right, I get that y squared equals 1 minus x squared, and then I get that y equals square root of 1 minus x squared. This is at least the positive solution for y. So that's going to give me, if I want to think of at least this part as a graph, this part has the equation y equals square root of 1 minus x squared. Okay? And so if I want to look at this area, so the red area is going to be equal to the area under y equals square root of 1 minus x squared from x equals 0 to x equals 1, right? Okay, I mean, listen, I know everybody knows the area of a circle, but have you ever thought about how you know the area of the circle? And the answer is it's probably never really been proven to you because this is going to be the proof of the area of a circle. Okay, so this is going to be the proof of the area of a circle, right? So we're going to see why this is. So how do we calculate this area? Well, at least for a quarter of the circle, we're going to calculate the area under this curve from x equals 0 to x equals 1, right? X equals 0 to x equals 1. Okay, so let's see what happens here? All right, well, how do we calculate the area of the circle? So we're just going to do, so the area, by what we've seen, the area, which equals the integral from 0 to 1 of square root of 1 minus x squared dx. Remember what this means. This is just f of 1 minus f of 0, where f of x is an antiderivative of the square root of 1 minus x squared. Okay. Well, I've done the work for you here. I've told you what an antiderivative of square root of 1 minus x squared is. Okay, this is the formula for an antiderivative of square root of 1 minus x squared. It's a complicated formula, but once you know how to do derivatives of inverse tangent and you use a lot of chain rules and quotient rules, it's a little complicated, but it's going to simplify exactly to this. So let me write this down on another page. So the point is that this is my f of x. So to calculate the area, I just need to punch in 1, and I need to punch in 0. So let's see. What's f of 1 over here? That's 1/2 times 1 times square root of 1 minus 1 squared. That's just going to be 0. Minus inverse tangent of square root of 1 minus 1 squared over 1 plus 1. That's just going to be 0 minus inverse tangent of 0. Inverse tangent of 0 is 0, because tangent of 0 is 0. So this is just going to be 0. Okay, so capital F of 1 is just going to be 0. Right, so this here is going to be equal to 0. It's capital F of 1. What about little f of 0? I just want to keep it on this page because I don't want to recopy the formula. Sorry, big F of 0 is equal to 1/2 times 0 times square root of 1 minus 0 squared minus inverse tangent of square root of 1 minus 0 squared over 0 plus 1. Well, the first term is 0, and the second term is the inverse tangent of 1. Does anybody remember what's the inverse tangent of 1 from trigonometry? What angle, when you take its tangent, do you get 1? Remember, it's the opposite over the hypotenuse. Sorry, the opposite over the
Yeah,
adjacent side. So when are they both the same? What angle?
yeah,
Yes, Abraham.
a tan of 45.
45, right? And remember, in calculus, we always use radians. So this is going to be negative 45 degrees, but in radians, that's negative pi over 4, right? Because we always use radians for calculus. Okay, so this f of 1 is equal to 0. F of 0 is equal to negative pi over 4. And the area, so this is negative pi over 4. So I'll write it on a new page. So the area of a quarter circle of radius 1 is, well, we saw it's f of 1 minus f of 0. And from the previous page, we saw that 0 minus pi over 4, right? We got minus pi over 4 over here when we calculated this complicated formula. And that is equal to pi over 4. And so the area of a circle of radius 1 is 4 times pi over 4, right? Which is equal to pi. Okay, and so this is the formula for the area of a circle, okay, of radius 1. And once you know radius 1, you can get any area, because if you double the radius, you're always going to multiply by the square of that, because it's a two-dimensional shape, right? So you can, maybe I'll just say similarly, you can determine that the area of a circle of radius r is pi r squared. Maybe we're not going to have time to do that today, but you can do that. But the point is, we figured out the area of a circle of radius 1 using calculus, right? By saying, first, we'll just do a quarter circle, because that's a little bit easier for the computation. So we'll do a quarter circle. And when you do a quarter circle, you get pi over 4. How do you get pi over 4? Well, you use calculus. The area under this quarter circle is going to be, you have to take an antiderivative of this function, which is actually not that easy, and we're not really going to learn how to do that this year. But at least we know the concepts. The idea is you take this function, you take its derivative, it's going to give you this. And so once you have that, you can just evaluate the area. Antiderivative at 1 minus antiderivative at 0. And when you punch everything in, you get that that's pi over 4. Okay, so that tells you that the area of this circle, this quarter circle, is actually pi over 4, which means the area of the whole circle is pi. Okay? And this really is the proof that the area of a circle is of radius 1 is pi. Okay? Because I think if you've seen pi r squared, usually that's not given to you with any proof. The reason it works is because of integration, because of this anti-differentiation. Okay, so another way of saying that is that if your velocity is given by square root of 1 minus t squared, and you run from time t equals 0 to time t equals 1, your total distance will be pi over 4. Okay, so this is going to be exactly pi over 4. Okay, so we're not really going to do any more integral calculus this term, where our focus is still going to be on differential and on sequences and series. Yeah, you could have done the whole semicircle, but the problem is that that goes to -1, and then you run into some trouble with the denominator here being 0. So it's easier to just deal with the quarter circle. So this is really all we're going to say about what's called the integral calculus. There's a lot more to it, these areas and volumes and everything, but I wanted to show how we kind of use intuition about physics to relate antiderivatives to areas. And once you've related antiderivatives to areas, you can use it to prove things in geometry, like the area of a circle. And in fact, you can do similar things to find volumes of spheres and cones and pyramids and all sorts of other shapes using calculus, using these antiderivatives. It ends up doing things. Well, if you want to consider 1/3 of the circle, that's a little bit harder because you can't really interpret that as the area under a curve. Right? So if you want 1/3 of a circle, that would be kind of like the green area here. And that is not so easy to interpret as the area under a curve, right? Because if I looked at this whole curve, that green part doesn't include this area over here. So 1/3 of a circle, at least with kind of standard integration techniques, doesn't really work so well. You can do it using polar coordinates, but we're not going to be able to do that now. Okay. So this is it. This is why the area of a circle is pi r squared, because you can use antiderivatives to figure it out. That's why it works. So it's a very advanced formula. People teach it as a basic formula for geometry, but the reason it works is actually very advanced. There's a lot that goes into it. You need to know derivatives of trig functions and how and the fundamental theorem of calculus and all of this to figure it out. Okay. All right, so that's it for today. So let me just say a couple of homework exercises. One of these involves a graph, which I need to give you a drawing of. So give me 1 second. Let me draw a graph here. So no, that's not what I want. Books. Where is the graph that I want? Okay, yes. Here we are. The velocity graph of a braking car is shown below. So we want to estimate how far the car travels when the brakes are applied. Okay, so this braking graph is going to be, I'm going to go draw some lattice points. So 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. This is going to be our time axis, and this is going to be 20, 40, and 60. This is going to be measured in feet per second, and this is going to be measured in seconds over here. And then the graph I'm going to draw in green looks like this. Sorry, let me draw that a little better. Okay. And the question is, can you estimate how far the car travels while the brakes are applied? right? I'm not giving you any formulas. So what you really remember, the distance traveled is the area under the curve. So this is just trying to get you to estimate the area under the curve here. That's problem number one. Problem number two is evaluate the integral from 1 to 2 of x times 1 minus x squared dx. Remember what this means. It means find an antiderivative, evaluate it at 2, and then evaluate it at 1. You may want to simplify this expression first before you do that. And then the third question is the velocity of a runner at half-second snapshots is given as follows. So these are the velocities after a certain number of seconds, and this is the velocities in feet per second. And the question is, what is a reasonable approximation for the total distance the runner travels in the first 3 seconds? So again, not a completely... Number 2 has one correct answer. These answers, these 1 and 3 are kind of about approximation. Okay? So there might be more than one answer that's more or less correct. Okay? But the question is to try to come up with a reasonable answer for these two questions. Okay? So that's it for today. So thank you as always for your attention. And next week on April 3rd, we're going to discuss logarithms and exponentials from a calculus point of view. So you do logarithms and exponentials in the pre-calculus curriculum, but we're going to talk about how they're actually related to calculus and where they come from. Okay, so we already know what a logarithm is and what an exponential is, but we're gonna relate them more specifically to calculus. Okay, so that's going to be the plan for next week. In the meantime, of course, I'll send out the notes and I'll post the recording on YouTube. Okay. All right. So any questions about stuff that we talked about today? Any of these velocity or distance or anything?
Yeah, hello.
Yes, Enoch.
Yeah, though I've been silent because all those things, these are things I'm always playing with. So I just want to give chance to other people to just kind of learn new things. So that's why I've been silent. But I want you to go back like page, I think page 16 or 7. Yes.
This one?
No, the next one. Go again.
This one.
No, on the side, either page 14 or 15.
Okay.
Page 14. Okay, yeah.
This one?
Yeah, yes. It's page 15, page 15.
Okay.
Yeah, but for this one, what if I wanted to give a note on this today, but actually my phone went off.
Mm-hmm.
What if, because you are taking the function they gave you and you which means it fall between 1 unit to 3 units. So you are taking the function f of 3 minus the function f of 1.
Mm-hmm.
So what if in short I just considered, because the distance between point 1 and point 2, that 3 units move, and the distance between 3 to the height of the graph it just some unit 9. Mm-hmm. So from here you will just say in short it just 9 minus 1 over 3. It will be so easy. 1 over 3 will still be the same.
Right, but I don't see how do you know, where do you get 9 minus 1 over 3 from?
Yeah. What I'm saying is that the unit between 1 to 3, because it gave you the area under the curve, and it gave you the bond of the function x.
Right.
Okay, so we know that the bond of the function x, which approaches from 1 to 3, there are 3 different units there. Are we sure, right?
Yeah, so it's three different units here.
Okay.
Yeah.
So there are 3 units. Yeah, so there are 3 units. There are 3 units there is the initial state, and that initial state is just 1 over the initial state, and from there again, from the point 3 up to the height, the measure is from 3 to 9. Yes.
Mm-hmm.
Yeah. So from 3 to 9, and we know that 3 times 9 is 27. So it's 27 over 3. So right. it will be 9 minus 1 over 3. So simple, what I was saying.
Right. Yeah, it is not. Yeah, it's 9 minus 1 over 3, but I guess I don't see the geometric interpretation. Okay, so one thing that you could do, maybe this is what you're saying. So if instead I drew the whole thing from 0 to 3.
Okay.
This is 3, this is 1, this is 0, this is still y equals x squared. then it's true, if I do the whole area, this
Okay.
part over here is going to actually just be 1 over 3.
Okay,
This
1
part
over
here
3.
is going to be 26 over 3. And the
Okay.
entire area, let me get a different color. So the entire area here, if I do it in purple, so the entire area here is going to be 9. Right?
Yes,
So
that's what I mean.
is
So
this what
now,
okay.
yes. So now the relationship it will only be between the 9 and the 1 over 3. So the height it will be the height minus the base. So it will just be 9 minus 1 over 3. That's why I'm saying the simple way because this one is also offered in the course that you can do EDMA 411 or understanding or analysis of circle and the area under the curve for plane surfaces.
Okay, so the point is, if you already know that the formula under y equals x squared is going to be 1/3 x cubed, if you know that this entire purple area is 9, then
Yes.
you can definitely say that this area over here is just going to be 1/3, and
Yes.
so you can do a subtraction. That's fine, but you
Yes.
have to know that. I don't know how to do that without calculus.
Oh, okay.
Yeah, right. I don't know
Okay,
how
sir.
to show that without using calculus. Yeah.
Okay, sir.
Okay. But it works. I mean, it's correct. Yeah.
Yeah. Hello, Andrew.
Question. Hi, Abraham.
Yeah. Thank you for today's class.
Right, you're welcome.
Stay encouraging all the teachers to continue coming to class until we can finish with this semester. Thank you very much.
All right, you're welcome. Let me actually stop the recording now.